non-recourse debt funded process through one of the large investment banks. And every month, whatever the customer saves, the customer gets a certain percentage of that, and the bank or the financial institution gets the other percentage, and that's how they facilitate their return on investment for these assets. This specific project's about 250 kilowatts. We did about 200 of these systems last year in California. Another great project that Imre mentioned. This is the Duke Energy 36 megawatt No Trees project that's co-located with their 153 megawatt wind farm out in western Texas. This project does have Dynapower equipment. This was, until the Aliso Canyon installations last month, the largest battery energy storage project. This is an example of a wholesale energy storage system where they're participating in the ERCOT frequency regulation and then also facilitating ramp rate control over the wind farm to reduce the impact that that very large wind farm has on the grid there. As Imre mentioned, so these batteries that you see here are the first generation batteries that were installed. Something we always caution customers, and Imre mentioned it as well, is to evaluate the commercial readiness of the technology. So when Duke Energy was looking to install this system, the first battery supplier said 10-year warranty, no problem. I think the company was maybe 4 years old. And then 2 years ago, 3 years ago, the company went bankrupt. The batteries did not last, and then Duke Energy had to spend significant out-of-pocket money to replace these lead-acid batteries with lithium-ion batteries from one of the bankable Korean companies, because it was a significantly higher commercial readiness factor, and that company has a $300 billion a year revenue compared to negative revenue, so they're also able to offer performance guarantees.
So are these your batteries on the right there?
Yeah. So what we specifically do is the power electronics. So these are the inverters that connect the batteries to the grid. So we work typically with battery companies or project developers, and then provide the power electronics. So Tesla, for example, has their batteries that are either coming from Panasonic or soon to be out of the Gigafactory. We're the electronics that connect the Tesla batteries to the grid, or the Extreme Power Samsung batteries.
So you don't make the batteries itself, you just do power electronics.
Yep. So we don't. That's a good differentiation. We don't make the batteries. We've worked with probably every battery technology you can think of. We have a tendency to talk about lithium ion like it's a single chemistry. There's probably 15 different kinds of lithium ion that are good for shorter duration to longer duration. So we shouldn't speak of lithium ion as if it's a single technology. There's quite a portfolio of chemistries under that. We've done a lot of work with the now defunct GE sodium sulfur battery, which was a DOE originated technology, compressed air, flow batteries, again, all in different levels from academic research in labs and institutions to 36 megawatt cash flow positive projects.
So with regard to the lithium ion, I think we heard that there's been some spectacular situations with some of those, and the varying chemistries that can be a part of that. Are there more stable, less stable? Where are they in terms of where people are going? I would presume we're going towards more stable, but can you talk a little bit about that?
Sure. So the picture that Imre showed has come up a lot. Specifically the Kahuku wind farm project, which Imre mentioned as well, which was a grid-tied energy storage project where there was a catastrophic failure of a battery. That was a lead-acid battery. Up until that point, everyone in the battery industry probably would have told you that lead-acid batteries cannot catch on fire.